Let's go into play from start. So good afternoon, everybody. So I'm going to talk about data analysis and visualization in Python, but I'm also going to really talk about reproducibility as well. I think that there are general principles that we can apply from what a variety that have come from a variety of fields, and there are ways of thinking about this to actually make what we're doing in terms of analysis, visualization, when we're looking at Python, to last, and questions that we either need to ask or we might want to ask. So as part of my background, I've worked as a software engineer. I've also done some training with the data carpentry training and also across Oxford. So I've covered a few areas that I want to draw from this. So first of all, we have some opening remarks. I want to look at the concept of irreproducibility. We never really talk about that. Think about some technical considerations about how and what we do, maybe some practical considerations that come out of this, and increasingly, as I've been updating this talk and thinking about it for this session, social considerations that come out of this, and how we can think about that this isn't just purely the technical aspects of what we're doing. So normally, I would finish the talk with this question: can somebody in your group or your lab reproduce one of your results using all the available information in the web or papers? And can you do this for their results? Essentially, I see this as an ongoing and a social process. But if somebody can start to do this, can actually take the information without asking you as a person or a colleague, and could take from that results, from the data, the software, possibly the hardware, and rerun, then you're in a good position. But equally, I think we need to challenge ourselves to redo this for our colleagues as well, for ourselves. But first, some good news, because we live in the bad news era at the moment. So if we've ever shared data, code, or research papers, then we're already beginning to be there. But we don't have, but something John Tennant says, which I think is correct, is we don't have to do it all the time. It's about knowing options. It's about using them when possible. And it's about continually making those small steps and trying to build on what we've got and trying to work through these problems, rather than having to make a big bang that suddenly we're all reproducible. It's a constant thing, and sometimes it may not be possible. Sometimes we'll just forget, we just don't have time, and we may have to come back to this and think about it. But it's okay. It's not some consideration of failure. But having said that, clearly, if it was all good news, then I wouldn't be giving this talk, and community of people working reproducibility through software, data, and so on and so forth wouldn't exist. Reproducibility is hard. It's very hard. It takes practice and it takes time. It might also be an ongoing process. Things that we worked on 2-3 years ago may suddenly stop to work. Why? Hardware, our systems update, our concepts of what we want to do update. So 9 years ago, when I was working on the square kilometre array testbed, or one of the early testbeds, we were building Puppet systems to reproduce our operating systems and get the right packages on the machines for our colleagues. And that was best practice. And then Docker came in, and after a 2-year change or so, we were all using Docker, in fact, building our own Docker repositories. And we didn't go forward, and in terms of what we were doing, we may not have gone forward, but we produced the stability for our colleagues, our scientific colleagues, to work on the testbed. legal and or practical reasons may stop sharing. So if one's using ethical permissions may not allow for sharing. If you're using human data, again, you may be stopped from sharing. And these are for perfectly valid reasons. So working on the museums project with some colleagues from museum and psychology, we wrote a little app that did some tracking of data. So we wanted to know how people with visual impairments touched a screen. So when they're actually trying to touch and feel an object which had been flattened, and we use swell paper to replicate paintings, we needed to know how they touched. The way the ethical data had been put together and had been passed through departments meant that we couldn't share it. So when we came to write the paper, the image that I'm sharing with you at the moment came from test data of one of our co-authors, was visually impaired and agreed to help us put some test data, and she was the original test subject, so we could actually validate whether the software was working. So we're able to reproduce that data about a year later, rerun all the scripts that we had and make sure they were correct. So you could then share software, share that little bit of data, just to prove that our method worked, but to also give other people the possibility of reproducing that if they wanted to. But we can't share the data that we actually got from the project itself. We also, I think, have to think about data size. If we're looking at data intensive processes, the data sizes and rates that we're getting, it may be impractical to actually share the raw data or the process data that we've got, except in certain circumstances. I suspect network admins would be rather miffed if we suddenly started trying to transfer petabytes of data, and probably quite rightly so. Secondly, using an algorithm is not the same as understanding it. I think we have to, just repeating a process isn't the same as understanding it, because if we're repeating it, all we're doing is putting in some data, repeat a process, and we get some results. But if we're really trying to reproduce it, then are we trying to understand the science, what the thought process that went into algorithms, into the process, into the way data is written and not written. And this takes process. It's not just a question of either understanding the algorithm as a pattern or the implementation of it, but actually don't really understand what's going on inside the pipelines. And then current practices of reproducibility often go against reproducibility. So we need, as Dan Katz points out, we need to find a balance between the cost of reproducibility versus the lost opportunity of new research, and the cost of not having that reproducibility versus the lost opportunity of future reuse. So in a sense, this is almost like writing tests for software. Tests for software and work on reproducibility don't necessarily move the field forward, in that you're not creating new things. What you're doing is you're working on making sure that what you've got that exists is robust. But clearly that takes effort away from new research. But then, is that new research or that way of moving a field forward, do we then lose it through not having that reproducibility? As in, if we can't reproduce results or we can't reproduce methods, then are we harming ourselves? In a sense, if we're looking at testing, can we continually test software to work out whether we've got bugs or we've satisfied a constraint? And these are not easy to mirror or to match, and there's a balance that has to be found through projects, through groups. And there is a cost to either side. But the question I've been asking myself more and more as I've been doing this, looking at this talk, and recently for other reasons is, what is it that we want to reproduce and why? And it's a question that we don't necessarily ask ourselves. There's a concept that we want to get to reproducibility. But what might we mean by reproducibility? So it can mean, I'm drawing here from Goodman et al.'s work in 2016, where he identifies 3 forms of reproducibility. Do we mean the reproducibility of results or replication? And by this, we take the same data, then we take the same method, and we should get the same result. It may be within a margin of error, and we understand what that margin of error is. But there, we're literally just testing the results. We can get the same result each time for a paper. Secondly, we might want to think about methodological or method reproducibility. So we start with the results reproducibility. We want it, does it take the same results? Well, then we try it with different data, not the same data and the same method. And do we get something that we would predict that comes out from the pipeline? In that sense, we're not testing results, we're testing the method. Is the method reproducible? These two, I think, are the 2 key things for reproducibility right now. And that's what we're all, I think, working towards. Can we find methods and ways of doing both of these types? So I put a 3rd type, which is mentioned, which is inferential reproducibility. And by this, we're thinking about, can we understand the processes that went into the interpretation? So if you've got your discussion, so we know we can get to results, can we then start looking at actually what is there context? Is there some meaning that's not computational that goes into that discussion? And can we surface this and make it much more obvious and open? The reason why I've kind of grayed it out is that this is a stage that is talked about, but I don't think we're actually quite there yet. We're moving towards it, but first we have to get results and methodological reproducibility correct first. And by that, I think we have to work out what we mean as well, what's acceptable to ourselves and our communities, and make that known. So how can we be irreproducible? So we can think the really big picture. Our methods sections talk about the 10,000-foot overview, or maybe the 1,000-foot overview for being really generous. We can be abstract about it. So we're not necessarily putting everything in. We sort of know what we mean, but we're not necessarily saying it. We can be short and sweet. We can kind of skip that little annoying process that we had to do, but it doesn't really matter that we had a bash script to do this. And we can include the deficit model to this. So we happen to know in our community that if we run function A, it always has parameters B and C. You may also be an expert in that part of the field, but that's fine. You don't have to share with anybody else. Just keep a certain amount of background knowledge to yourself. And above all, don't share. Don't share the data. Don't share the code. The paper should be absolutely everything. And that all comes together in bubble into make sure that you cannot reproduce your own work. I would say it's die, but it's their skills that are their ways of thinking that we occasionally may fall into that we don't necessarily think about it. Certainly science technology scholars have called this tacit knowledge. So the deficit model, there's a community understanding of a certain concept, and it's not necessarily made clear in a paper. So how might we think about doing this? Version and sharing our software and code, even if it's not clean, is important. It's vital. Document the version changes. So if we have software, think about semantic versioning. So 0.1, 0.11. If you have a minor update, 0.12. If it's a major update, then it becomes 0.2. And document why you've made the changes that you've made and what you've done, and have an update policy. And version control. Most of us are aware of GitLab, Bitbucket, GitHub, Subversion, so on and so forth. But make sure they're known and they're public. And same with data as well. Version data. Figshare and Zenodo certainly are very good options. I have to say I haven't used Dryad. But does your institution or group have preferred options? Does your institution actually have their own version? They may have a repository that's essentially a skin over something like Figshare or Zenodo or what have you. So maybe work with your library and your institutional infrastructure here. As part of this, code and data does need a license file as well. If you don't have a license file, then somebody can't use your data or your code. They don't know how to do it. So just make it obvious and make it open. I really wouldn't recommend ever writing your own. Again, does your institutional group recommend a particular file or type? Citation, allow, if you want your software to be reused or to allow other communities and labs to reuse the software that you're doing, your data flows, then actually make sure that it's citable. Otherwise, they can't reproduce their work either. This isn't just a question of what somebody does to you, but it's how you support other people. So Figshare and Zenodo offer integrations with GitHub, certainly, GitLab, I believe, to put in digital object identifier, which allow your software to be, whilst the DIY system is running, traceable if it moves. And if a paper does use your software or part of it without credit, then please do contact the editor. This has to be more than just one lab. This has to be a community process that the community has to learn and work with each other. Software source as well, so cite the software as well. It's not just a question of, I have a method and here is my method, and maybe here's a doc file. I actually describe the software. It's a first-class citizen in this arena. And make sure the software has a DOI. Maybe you want to think about a software paper as well, such as the Journal of Open Source Software. But also make sure the software and the data themselves in their original are available and they're citable. And even if they become unavailable, they'd be hidden, provide in, or they can't be shared in their entirety, at least provide a reference, a DOI with this so that it's traceable. And this sort of all comes together into being fair to each other and ourselves. So findable, how can we find what we've described? Accessible. So is it by a standardized protocol? If it's interoperable and reusable as well. So reusing languages and vocabularies around rather than trying to implement your own every time. If something needs extension, then try and speak to the original vocabulary. And make sure it's reusable as well. And this is about looking at things like provenance, data, attributes, and make sure that you're talking to your own domain community standards. But here in terms of practical flow, what kind of things can we do? Start scripting work. So maybe you start with a simple bash script. You then start putting together Python workflows. So you modularize your code, start putting it together into much more deeper and better flows. Or you have one top level flow that actually covers all of your, or one part of your workflow and your data analysis. Make notes on the data sources and processes as well. So if you're creating data, how does it come to be? So the W3C Prov data model here is very good for doing that, I think. It provides a way of saying, these processes created this data. And from that, you can then link the processes out and begin to think about inspecting it. If you're so inclined, then perhaps continuous integration can help you, since automating build and tests means that you can then actually run test flows and test data. And I don't say this is a panacea, but then also making the workflow clear and available to everybody. So we build workflows, they change, they will emerge. Nobody comes out with a particular workflow that is suddenly perfect first time round. But as long as they're available, then I think they also have another communal support. And also noting your dependencies and package versions. So if you're using, say, a Python virtual envelope, then pip-freeze redirect to sonic requirements.txt means that you'll then capture the packages that you're using within that particular workflow, and you can share the requirements file with somebody else. So if they're rebooting a virtual envelope, can then use requirements and rebuild with those packages and the package version numbers. As part of this, Docker, although of course other systems are available, has been one of the successes, if you will, which comes with its own challenges. And certainly, I think the fact that it uses a Docker file is super useful in that you can describe the version of the operating system that you're using and its version as well. So say Ubuntu 18.04 or 20.04 as it is now. Although some people do put in Ubuntu and then latest, which is fine for 3 months. But then if you're trying to rerun something 2 years later and you get a completely different version of the operating system, you could get different packages. But the file also helps support your documentation by listing things like the dependencies. It tells you exactly where data is being read in from, what it's being read out to. It allows development to happen locally, so I can pull a Docker file and Docker machine onto my laptop or a local desktop, and then I can push it back remotely. And we can share that, and we can put it into version control. But it also potentially helps us break down big monolithic pipelines into much more smaller workflows and to pipe things together, as well as ultimately being versioned. So we know we can change things, and then we can say on the version 0.2, our Docker file changes. Certainly some projects are currently using, such as LIGO, have been using Binder. Partially as outreach, it is used for as an educational tool. Essentially, this is just an online service that allows you to link a GitHub account into, and it builds a Docker container, so you can actually rerun an entire workflow. And that may be useful for a paper or a conference. It's something that I've used for teaching. And it allows you to define a state of a machine, so all packages, the version of Python, and to have that rebuilt automatically for you. It's not foolproof, but it can be useful. And that sort of leads us into literate code using Jupyter, but I say pretty much the same using R Markdown. So literate code, we're thinking about binding both text and code together. We want to tell a story. We're trying to document the process that we've used and not just our results. Why have we made certain choices? Why are we using certain parameters? That allows us to note dependencies again. modularize our code, build pipelines actually within the notebook, potentially. It can be version controlled, and above all, it can be shared. Can somebody else run our notebook? And it's something that I've used in the past doing a visualization experiment just to see if I could build a social network for some computational social scientists as an experiment, just to see whether certain tools that we were playing with would work. And it meant that I could share that data and give them a PDF fairly quickly. And we could work out whether we actually wanted to go on doing that or not. But it also meant that you can then experiment with that thing and describe what you're trying to do to people who don't necessarily know your work. They may know the field, they may be interested in the results, but they may not know exactly what you're trying to do. And finally, in this section, tell me about it, tell us about it. You know, write blog posts or tweet it, or a post or a conference paper or journal article. Above all, we need to communicate what we're doing and how we're doing it. Otherwise, we're writing an awful lot of documentation and making sure our documentation is sterling, but we're not doing anything with it. And this, for me, is the new bit, certainly on this talk. And this came out of a conversation I had 2 years ago in Oxford. So not all projects or pipelines will run forever. We'd love them to. We'd really love them to. But we need to start thinking about, how do we plan for endings? How do we plan what we're doing so that if our funding does stop for whatever reason, or what have you, we can bring things together neatly and nicely so that it can be built on. And what the work that we did is reproducible, is still runnable, and could be moved on. And part of that is the documentation I've been suggesting. Right. But we have to think about, so we can do this in two ways. We can almost do the Google option, which is to run everything all the time. So we take all our software and we have continuous integration that runs constantly, rebuilding ad infinitum. But that also means that we're then tied possibly into using particular hardware if we have hardware that we have to use. It also takes a huge amount of compute resource. We're talking, certainly when Google do this, they're doing massive amounts of computational years within a short amount of time. Or we can acknowledge that repeatability, if we think about in terms of reproducing results, is limited. That things will happen, updates will happen. Software is updated, hardware is updated, the data format changes, or the XML schema or linked data schema changes. And these things happen over time, if we're talking 10, 20 years. So perhaps we want to make our process inspectable. And by that, I mean examining the computational provenance records that are provided by the project. So what dependencies did we use? What hardware was used? What pipelines? What data formats? And from that, it should be possible for anybody who's in the field to reasonably be able to reproduce what you did mentally and to work out whether it was practical or whether it was feasible or not. And it's a challenge, but I think it's certainly something that we should be thinking about, that our documentation is not just for ourselves, but to imagine that time when we're not here, or within a decade time when things end, if we're going forwards and then actually you think maybe there are lessons to be learned, we can at least find them. And for this, I think we should be building communities within our own labs, within our own groups. So encouraging sharing and reuse within certainly our defined spaces. If somebody new joins, then can we get them to build and run a pipeline? Can we get them to think about reproducibility as part of their process, not just as something that we'd like to do right at the very end? So how do we keep that process going on, that kind of process going on as new postdocs come in, people leave, and then they can go to their group and bring in those and spread those practices as well. And if needs be, then think about training through the carpentries, data carpentry, software carpentry. The tools are basic, they are general, but they're really good. I think they're very good and very worthwhile tools and ways of thinking. They're about ways of thinking about how this through. And perhaps talk to research software engineering groups. So I believe there's a big German RSE group, and also related communities to share process of what you're doing. Maybe you can learn from them. Maybe you can help with their standards and they can help with yours. So we can actually all move to making this shareable between us. And I'd like to leave you the final thought that you may not ever achieve 100% reproducibility. And this is probably okay. It's a great goal to have. It would be lovely to do this, but I think we'd be challenged to actually make it happen. Certainly given the constraints that we've got between reproducing and making sure what we've got is stable and getting new and finding new cures, techniques, and new research, new questions to ask. So thank you very much for listening. I'm happy to take questions here or afterwards, well, via email.
Thank you. Thank you so much, Iain. That was a very, very valuable talk, and you've touched most of issues out there about reproducibility. I loved when you mentioned about that this is a community thing, that we all should change how we look at sharing and making our resources available. Also, there's another issue about researchers have over-embarrassments about sharing their what's so-called ugly code. So there's so many researchers, they just learned how to code it and they just wrote that code so quick and it works, but it's not elegant or also like does it sound professional? Do you have some advices or something like that for researchers who just have this worries about I will be shamed for my ugly code or something?
So yes, I've gone through, this is where version control is really good. So you can get your code into version control really quickly and share it and then tidy it up as you go through. Part of it is you just have to do it. It's horrible. I've got code out there that I've put up and I've linked to from papers and I can look at now and I kind of cringe. But then it's the code that worked for the paper. So I sort of don't want to, so in that sense, I don't want to touch it. But I think we just really, really have to just jump at it and do it. Nobody starts off writing beautiful code first time around, or if they are haven't met them, but also they're also very, very, very rare. Keep them.
Yeah, thank you. We have a question on our meeting map. It says, do you have any recommendations for good tutorial Docker or other containers, or what's the best way to start there?
So best start. I learned by trial and error. I was talking to. When it started, we looked at it with myself. I was working with a colleague, and we were sort of, are we sure this is going to work? And then we started putting things together, and we took we knew we had one small process that was discrete, and just went, well, actually, can we get this Dockerized? And can we put this in a Docker file? And one of the advantages of it is that you can create the file locally on your laptop and try it. And if it doesn't work, you can just delete the Docker file and delete the whole thing, and you're not going to do anything to your machine. Or you're unlikely to do anything in your machine. There are ways, of course, of passing through to hardware, but it's I'm very much of the try it of the try it school. I've been slightly out of that area for the last year or so. So I know that, and if you're looking at high performance computing systems, HPC, some administrators won't allow you to run Docker, but they will run Singularity. So Singularity is very similar. It'll suck Docker files into it. It basically solves some of the security problems Docker has.
Great.
So SK was very much in a closed system, so they could just use Docker.
Yeah, good. Thank you. Jonathan commenting, this talk was really great. Can you further explain training by carpentries, please?
Yes. So that's there. I'm thinking of software carpentry and data carpentry. I'll see if I can get their URLs. And they're very much training by and for, so that's one. So very much training for and by scientists, and they're about doing things like how do you work with data. And they're very simple. You start with, say, CSV, you do a little bit of some Python or some R, some visualization, a bit of working with databases. But it's not just how to, so it teaches you how to, so software carpentry is about how to improve your code. Data carpentry is more about how you deal with data and keep your data nice and clean and good practices there. It's the slightly brought it together in just terms of the carpentries now, so both are together. So that training is a 2 or 3 day course. You get a couple of trainers in, some helpers, and it's very much hands-on. So it's not just we talk to you; it's we'll actually live code, give you exercises, run round. It's a fun couple of days, but exhausting.
Indeed. Thank you so much. Also, there's a very like a big point I found in research more than, or like in academia, more than any other sectors, which is over worries about citations and intellectual priorities, and somebody gonna steal my work and somebody gonna scoop my efforts or something. There's a big reason of it. It's these journals and their impact factors. That's the more citation you got, you are then the best one. And this event, one of our motivators was, yes, to contribute to the community and to raise flags that researchers should be weighted over how much did they share, how much were they open, how much they were open access, rather than how much like a big media hit they were. So what do you think, how can we help journalists to recognize the issue about change your impact factors and make guidelines for open science and for sharing, rather than for how much citations a paper could get?
Yeah, I think that's a really important point, and I think it's building on the pressure of making sure that journals allow you to publish both code and software. Talking to colleagues of mine who work in visualization, and the amount of journals they have who don't want who just want the pictures. They don't actually want the software that created them, and that's really the important bit. I think we need to certainly press for code to be a first-class citizen. As I said, a first-class citizen. It's not subordinate to the paper. It's actually part of the paper. This is one of the reasons why I sort of like the Journal of JOS, or the Journal of Open Source Software, or Journal of Open Research Software, which is what I published in a couple of years ago. That they want the data as part of it. It's not, it's you know, and the work that I've been doing recently is more theoretical, but that was the last time that we were able to publish all the data and all the software and know that we were happy in that. We also, I think, have to look at funders as well. Do funders really understand and really engage with open source, open access, and what this means? But it also means over time, and it's the bit that I didn't talk about, but I think is there, that we publish data and we publish metadata and we publish software. Things move. Systems practices change, software moves its locations. So how do we, in part of it, I think that's where we need to think about concepts of archivability, that say, actually, this was all here, but now it's now moved from Subversion, say, through to GitHub. And that was the big move about 20 years ago. So that's, you know, a lot of many projects were in SourceForge, and then suddenly GitHub became big enough that quite a few moved to GitHub. So you're then losing those links. But to also think about the long-term infrastructure for putting in data repositories. And that's where I think the FAIR principles, which I linked to, are really good. They're really helpful, because they're about actually making that linking happen. If we can get those more and more bound into our communities, funders, and our journals, then that's where the pressure take. But it's going to take some time. Yeah, it would be lovely if it all happened tomorrow. You need to do this, would be great. But I'm a pragmatist. I've been around. I think, like everybody, I've been around. We've been bitten by this before. So, yeah, I think a lot of it is how do we. But it's also not just at that level. It's also when we point people to our software pipelines and our data pipelines, we just say, how did we clean data? What did we do? If we've got we change our ugly duckling code into a much more beautiful duck, we just show that change happening over time. But also it means that if a bug comes in, we can at least find it. I know of at least certainly a piece of software where I believe there's a version up to version 5 reproducible. Suddenly something happened in 5.1 and everything broke, interestingly, and it was then fixed in 5.2. That bug had been introduced that nobody had fixed. So it's a I think it's a multi-part question. And I think everybody should be trying to do this. Certainly from where I've kind of moved into digital humanities and computational social sciences, we're kind of moving, we're a long way off this. There are a few of us shouting that we should really be doing this, and we're kind of, I think we're where many scientific communities were 10, 15 years ago.
Yeah, thank you. Thank you so much. Do we have any other questions for Iain from the participants? I will check our pad again. Okay, we read that. Thank you, Zishan. Zishan is clapping for us. So thank you so much, Iain. That was a very valuable talk. We thank you so much. And this was our last talk for today. And tomorrow is the last day in Data Week. Please stay with us. We still have very interesting talk for tomorrow talks. So we will start at 10 a.m. With Dr. Roxane Lefredi, and she's gonna talk about temporal-based dynamics in invasive recordings. After, with Professor Kirsten Ritter in next level medical imaging analysis. Then Shams Tabriz will talk to us about Git, versioning, and software test best practices, and he will discuss GitHub as well as a approach. Ilya Opyankin will talk to us about building high availability architectures in SQL. And then we have Professor Amr Awad to talk about next generation data centers and high performance computing. And by the end, Christian Malkins will talk to us about large scale IT infrastructure, reliability, and scalability. So that was it for today. Thank you so much for being with us, and we are looking forward to see you tomorrow. And I wish you a lovely rest of the day. Bye-bye. Cheers.
Bye. Cheers.